Okay, so you hopefully have had some time to figure this out. And the skill you need to remember is, of course, I assume you have already figured this out, right? What is that thing that you have to do to get the answer to this? Well, because everything here is written in terms of squares, right? You need to get something squared. And when you have some loose terms like negative 6y and positive 8z, what you need is to complete these squares, right? So how do you complete this y square minus 6y? Yeah, of course, you have to add 9 because that's half of 6 or half of negative 6 squared, all right? So that would make that into a complete square. And of course, the golden rule of equation says do unto one side as you would to the other side. So you have to add 9 to both sides if you're going to do that with one side. You have to be fair. And then half of 8 is 4. 4 squared is 16. You add 16 to both sides. And what this allows you to do is, of course, and I know you have seen this before because you know, we teach the same thing in beginning intermediate or algebra class or college algebra class. All right, so it's x squared plus y minus 3 squared plus z plus 4 squared. And so again, this is going slow here. The other side is 25, right? And of course, the radius is not 25 because you have to take the square root of that number. And so this is 25. All right, so you get the answer. First, the radius is 5. That's why you see 25 on the right-hand side. And then the point, the center is, okay, and this may be counterintuitive, but remember you have the negative sign in front of the x naught, y naught, and z naught. And that's because we are finding the distance using the distance formula. And so the center for this is 0, 3, and negative 4. Okay, you have to sort of to change the sign of that number that comes within the parentheses. So I hope you got this correct answer. This is not too difficult. Let's move on to the next part. All right, so before I finish this section, in order to help you do your homework and everything, I should mention a few things. All right, so first, how do you tell when 3 points in 2 or 3-dimensional spaces are on the same line? Okay, so we call these 3 points collinear, right? Collinear means same line. And I think, of course, I misspelled it. It should be 2 L's. I'm not sure why. But you say 3 points are collinear, meaning that they belong to one line, only if, how would I describe that in terms of vectors? Okay. I think you can see this from the picture. If PQ and PR are what? Okay, the distances, I mean, the lengths are different, of course, but they must be parallel to each other. Okay, now they could be going in the opposite direction, but remember that still is considered parallel. So 3 points are collinear if and only if PQ is parallel to PR. And of course, these are also parallel to QR. And of course, you can reverse the, you know, the vectors. So you can call them QP and RP and RQ. They all have to be scalar multiples of each other. All right. So I think you had a homework question that involves this. All right. The second note I'm going to give you before we finish this section is this fact. Okay. Now this is actually a very important fact. It has to do with the idea of linear independence and spanning sets in linear algebra. Some of you may have already had a linear algebra. But if U and V are not parallel and they are 2-dimensional vectors, non-parallel 2-dimensional vectors, then every vector in the 2-dimensional space on the plane can be expressed as a combination, more technically, linear combination a super important term in linear algebra, a linear combination of u and v. And all that means is that you have some scalar times v plus some scalar times u is equal to that, the vector that is given to you. Okay, so let's say you want to express the vector 3000 comma negative 425 or something. Okay, so that means that you can, what this statement is saying is you can find two coefficients, two coefficients a and b, so that you can write that equation, write that given vector as, you know, au plus bv or something like that. All right, so here's an exercise. Let's do this together. U is 2, negative 2. Now you can see this, see here. Okay, so this is u, 2, negative 2. You can see that right here. And then v is 2, 5. Okay, so u and v are clearly not parallel. And that means they are linearly independent and they span R2. Those are technical language expressions from linear algebra, which you are not responsible for knowing for this class. But you should be able to write any vector on the plane as a combination, a linear combination of this u and this v. In particular, here's the question. Let's try to write the vector negative 2, negative 26 in terms of u and v. Okay, you see what you have to do here? All right, so you can opt to pause this and then come back with it. I think you will realize, or maybe you have already realized, this will include some sort of a system of equations or involve systems of equations. All right, so this is what you will do. You're going to express this as, let's say, AU plus BV. Okay, because that's what we mean by a linear combination. And of course, that just means it's A times 2, negative 2, plus B times 2, 5. And you can also do better than that. You can also write this as 2A plus 2B and negative 2A plus 5B is equal to negative 2, negative 26. In case you're wondering, because there is this significant lag, I'm just writing with my stylus on the screen that is blank, and I'm just keep writing, and then I'm waiting for like 10 seconds until what I write on the empty screen appears. It's very frustrating. I hope I can fix this sometime soon. All right, so AU plus BV is equal to this expression. All right, so it's 2A plus 2B, comma, negative 2A, I hope it's not come back. Yeah, negative 2A plus 5B is equal to, and we want this to be equal to negative 2, negative 26, right? So you got it, right? So 2A plus 2B, or not 2B, is equal to negative 2. And then negative 2A plus 5B is equal to negative 26. And so it comes down to a simple, sort of basic algebra problem called a system of linear equations, right? You probably learned how to solve systems of equations like this one here. And you can do substitution method, you can do the elimination method, you can graph these, both are straight lines, find the intersection point. What else can you do? Or you can use Kramer's rule if you remember what that is. You can use Gauss elimination method or Gauss-Jordan elimination method with matrices, all sorts of things. I think the best way to solve this particular system is just simply add these two, right? Because you can see 2A and negative 2A will cancel, fortunately for us. So if you add these vertically, here in this middle column, you have the first column is 0, and then the second column is 7B, and that's equal to negative 28. Such a nice number because I wrote the problem. So that means B is equal to negative 4. And by the way, I hope these 3 dots will make sense to you. I should have included this in our basic notation handout, but the 3 dots you see here means therefore, okay, or the conclusion mathematically is B is equal to negative 4. And then you can plug this into what? Plug this back into maybe the first equation, it says 2a plus 2 times -4 is equal to -2. And that should tell us what that a is, because this tells me 2a is 6. A has to be equal to 3, right? And then you can verify, check your answer. 2 times 3 minus 2 times 4 is clearly -2. Okay, so this tells me then -2, -26 is this vector, which is the linear combination of 3 times the first one minus 4 times the second one. And that is the answer to that question. And you will have something similar on your homework, I believe. Okay. Again, there's no difficult algebra involved in this besides what you probably studied in your beginning or first algebra class. All right. But the fact that every equation can be written this way, a linear combination of two, is something that is very, very nice. In three-dimensional space, you will need 3 vectors, 3 non-parallel vectors, technically called 3 linearly independent vectors, to be able to write every vector in R3 as a linear combination of those vectors. Okay, finally, let's just do a little exercise. What is this? This is later we will study this as a vector valued function, but t is this random, input value, or in this context we call t the parameter. But what kind of curve is this going to draw as t goes from -infinity to +infinity? Okay, so here's my x, here's my y, here's z, and of course z is always equal to 0. And you notice here x squared plus y squared, and you will be doing this many, many times, okay? Because you will see lots of sines and cosines in this class. And when you see sine and cosine of the same angle or same number, you almost always try to square them and add them, okay? In this case, x squared plus y squared is equal to 1. How do I know that? It's called the mother of all trigonometric identities, right? And it's always going to be true. I mean, it's 70 years from now in your deathbed, if your grandchild asks, hey, what's cosine squared plus sine squared? And you can say it is still 1, okay, because it's not going to change. Anyway, so what is this? Well, if this is a three-dimensional space, and it is three-dimensional because it has 3 components or 3 coordinates, this one just tells you that as t changes, if t is equal to 0, you have this point 1, 0, 0, right? And the fact that this is satisfied means that every point of this function is going to go through and going to be on the circle. So that z is always 0 because of the third component. And as t moves from 0 to infinity, for instance, it'll just be going around and around and around. Okay, so that's a way to understand what is called a vector valued function. This is something that we will be studying extensively in chapter 3. But at this point, I just want you to be familiar with how to write and describe vectors, both visually by sketching, and also algebraically in terms of equations. Okay, I think that's it for this section. Next time, we'll be answering this very important question. How do we find the angle between 2 vectors? How do you project one vector onto another? And all of these things and many other questions can be answered by one simple operation called the dot product, or the Euclidean inner product. Man, that sounds really fancy, but you would have to wait a little bit until chapter 3, or chapter 2, section 3, to answer these questions. That's going to be a great section. Okay, so until then, I hope you have a great day, and I will see you then. Bye.